All right. Hello, guys. 27th of August, 5:51. Let's do another LeetCode problem today. Had quite a busy day, but we'll still try to do pump one out today. It's going to be number of islands, so given an n by n 2D binary grid, which represents a map of 1, which is land, and 0 water, return the number of islands. An island is surrounded by water. All right, just one second. So we're going to do number of islands. An island is surrounded by water, and then we need to count the total amount of islands. So here is one island. So just one island is all it's set by 0. So this is a typical graph problem. We can either use a breadth first search or a DFS to search this problem. For now, I'll be using a breadth first search approach, which will use a DQ. It's going to use a Q to solve this problem. First thing, we need to have a integer, a variable for the number of islands count, and that's what we'll be returning at the end. But other than that, we'll be iterating through each of the grid. And if we find one, we'll append that coordinate to our queue. And then while there exists a queue, we'll pop it from the queue, and then we'll initiate a BFS, which will look around to it. We'll first change the 1 to a 0, and then we'll look at the 4 horizontal or vertical squares next to it. And if it is a 0, it's going to enqueue that to the queue, and then the queue is going to keep on continuously following until the whole entire island has been found. So yeah, does that sound good? Sounds like a pretty reasonable approach to me. So why don't we go ahead and start coding this up? So first we're going to have a variable called island of islands, initialize this to 0, and then let's find out how many rows we are. So the length of the grid is going to be n. This is the amount of rows, and the amount of columns we are, which is going to be n. And then for this, we can look at any row because they will all have the same amount of columns, but we can do m. Then we're going to have a queue. Let's use a dequeue so that we can pop left, or we can use a simple array as well. Doesn't really matter which one we pop from first, but a dequeue. Why is a dequeue better than a queue for pop left? Double link this. So it's like a LRU cache. I see. So it's going to be a constant time thing, where I think for a dequeue, if we pop it, we simply change the pointer to the element after the first one. Whereas for a normal list, after we pop it, we have to shift everything back left by 1. And then let's start our traversal. So for row in range n, this is not going to include the last one, so it's not going to give us index out of range error. And then for column in range m. Now we're going to check this grid. If the grid is indeed, if it's a 1, that means we have found an island. So first thing we have to do is we need to increase the number of islands that we have by 1. And then we need to set this exact grid to 0. Now it's important that we set it so that when we do get into the queue, let's say we move over to the right, if we haven't set this original grid back to 0, then then the new grid that we're going on is going to think, oh, my left one is a 1 as well, and then potentially there's an error that's going to cause well, it's just going to infinitely go on. So after we set it to 0, we're going to make sure that we append this to our queue. Let's append it as a tuple. It's going to be a row column tuple. Then after that, we can check our queue. So while some entity exists within the queue, we're going to get the row in column coordinates equals q dot pop left. Doesn't really matter which way we pop from, but we can pop left from here since we're using a dequeue. Then now that we're here, we can simply look around it and append it to the queue if it is 0. So first thing we need to check is if is the x, are we at least, so let's say that we want to check the left. That means we need to first check, are we not on the 0? So x greater than 0. And then we have to check if x grid minus 1 is equal to 1. And if that is the case, we're going to first set that grid to 0, and then we can append it to our queue. We're going to append a tuple, which is going to be x minus 1 and y. Another case that we can check is if x is smaller than n. So n is going to be the length of the grid. N is going to be the length of the rows we have, right? Wait, actually, let's see what we have to check. It's actually going to be m if x is less than m. No, actually, no. So x is the. So what was I saying? For x more than 12, we're going to look at the rows. So are we at least this row or greater? So similarly for this, we need to check if we're not on the last row. So if x is smaller than n minus 1, so n is going to be 4 for this, and it's going to check 3. So we want to make sure that we're at 2, at least 2, right? Because if we're at 3, then there's no way we can check for one more. So we're going to make sure that we're at 2. So if x is smaller than 3, so at 2 it'll go sense, but if it's 3, it won't. Yeah, that makes sense. And we're going to check, is the next part of the grid 1? And if it is, similar to this, we're going to set it to 0, and then append it to our grid. It's really important that we set it to 0 first here and not up here, because if we don't set it to 0, then other grids might, add a queue that is like we might add it to the queue and it hasn't been changed yet, but then another grid might see it first, and that grid might be populated, might be processed first, and they might add the same grid again. Another thing that we could do is add have a set of scene hash set of all the scene coordinates, but this way is a bit more easier because we eventually do need to change it to 0 anyways. Now we can do the columns. So if our y is greater than 0 and our y minus 1, so this means for our columns, if we're at least from the first column, then similar to before, we're going to set this to 0 and append this to the queue as well. And lastly, we'll simply be doing this for, yeah, so if it's less than m minus 1, so m in this case would be 5, but we need to make sure that the last thing we'll check is 3, 0, 1, 2, 3. That's going to show that we're going to do that. Set it to 0, and then we're going to append that to our thing as well. And then this queue is going to continue to go on for any given island that it has been first found on, and then once we're done, we can return the number of islands. Then we'll be able to see that our BFS has worked. Now let's try to do number of islands, but using a DFS approach. So that was our BFS approach. Let's do a depth first search approach. So for say DFS, we'll be using recursion, where we get to 1, and then we're going to go all the way to the left and change it all to zeros. And then for each step, we're going to go left, down, left, right, down, and up. Similarly like before, we just have to make sure that before we go on to our next iterative, that we do change this current grid to a 0. So with the DFS, we can use a recurse helper function, but first let's set up our initial code. So we're going to have number of islands. And then similarly like before, we're going to find out the length of our rows and the length of our grids, the length of our column. And then we can start iterating through these for row in range n and for col in range m. If the grid that we are on right now is a 1, first things first, we need to increase the number of islands that we have. And then we can call our recurse function. And we're going to send in our row and we can send in our column. And then after all this, we can do return number of islands. Let's actually put this recurse function inside here so that we can mutate the grid. So that we can mutate the grid directly rather than having to copy over the grid. So for a row, we're going to take in a row, which is a int, and a column, which is also an integer, and it's not going to output anything. Yep, so that sounds fine. So at this point, we assume that we are at a proper grid. So first we're going to do is going to set this point to 0. And then after that, we can simply do a recurse function. So if, similarly as it before, if the row is greater than 0 and the element to the, well, the row above this is equal to 1, then we can simply just call the recurse function again. Similarly, if row is smaller, oops, is smaller than, I don't think we have access to that, so we're going to do length of grid minus 1, and grid row plus 1 column is equal to 1. Then we can call recurse on row plus 1 and column. If column is greater than 0 and grid row column minus 1 is equal to 1, we can call recurse row column minus 1. And then if column is more than length of grid of the first element, which is going to be the length of the column, and grid row column plus 1 is equal to 1, then we can recurse on row column plus 1. So let's try that out for the DFS. Oops. Accepted, and if we run it, we should get accepted as well. So that was our DFS and BFS approach. Both are quite intuitive, I guess. This is quite a typical number of islands is a quite typical graph traversal problem. DFS. BFS, I guess it's really up to you. I think BFS comes to me a bit more naturally, only because we don't have to use recursion. So the case for this recursion is we find a grid, we go to the far left, and then after it's done, on the one just before we start going, we go to the far top. And then if we can't go anymore, we go to the far bottom. And then once we're at the bottom, we're going to go to the far left, and then after that, we're going to go far right. So this guy is going to go to the bottom, to the most top it can. So yeah, this is going to look like quite a funny. Let's see what this might look like for the recurse. Okay, for the BFS, it's going to be this guy, and then this guy, this guy, this guy, this guy, this guy, this guy. But for the DFS, let's see. So we start here. We go to the very top. We can't go anymore, so we go bottom. And then we can't go top because that's already been changed, so we go bottom. And the bottom point, we can't go top, we can't go bottom, we can't go left, we go to the right. And then at this point, we go up, and then we go up. At this point, we can't go anywhere. We can't go up, we can't go down because that's 0, that's 0. We can't go left because it's already 0, so we go to the right. And then there's only one way forward here. So it's going to look like a loop for the DFS. Cool. Hope that makes sense, guys.